Suppose we have a inwards magnetic field, so that's going to be represented by a series of x's. And we have a positive charge that enters this magnetic field at some velocity. We know from our right-hand rule, if we point our fingers into the screen and our thumb in the direction of the velocity, our palm is going to be pointing upwards, so this charge is going to experience an upwards force at first. But we want to see what happens after. So since it experiences an upwards force, it's going to accelerate upwards until it's moving upwards. At this point, we can use our right-hand rule once again. Now our fingers are going to be pointing into the screen, our thumb pointing upwards, our palm is going to be pushing to the left, and so the force is going to be towards the left. So our charge is going to accelerate towards the left until it is moving to the left. Once it's moving to the left, once again, use your right-hand rule. Fingers pointing into the screen, thumb pointing to the left. Now your palm is pushing downwards. And so the charge is going to accelerate downwards. Once it's moving downwards, we can use our right-hand rule one last time. Our thumb is going to point downwards, our fingers pointing into the screen, our palm is going to push to the right this time. So our charge is going to accelerate towards the right, and it appears that it travels in a circular path. And so it turns out that any charge, provided that it's not moving parallel to a magnetic field, any charge that enters a magnetic field moving at some velocity moves in circular motion. And in our case, we're only going to consider the 2D case in this course. So 2D case, where the angle between the force and the velocity is always going to be perpendicular, which is true for all cases. So theta is equal to 90 degrees. But we only need to consider two components since we're working in 2D. So we have an x component, if you will, and a y component. If we didn't, then what would happen is that one component would accelerate. So suppose we have our velocity like this, and our field is off to some weird angle. So if this is the y-axis, this is the z-axis, this is the x-axis, and our force is not completely in one of these axes, then what happens is you have to deal with components and you have some helical trajectory. But since we're working in 2D, we have uniform circular motion. So if we draw our circular path, at any point the velocity is tangential to this path. And if we use our right-hand rule, or our knowledge of the magnetic force, it's going to be perpendicular to this velocity. And so for a positive charge, we can see that it's going to be pointing this way. For a negative charge, your circle would be going in the opposite direction, be going like this. But we'll get to that. Now we want to derive an expression for the radius of this circle. So we know that the magnetic force FB is equal to the charge times the magnitude of the velocity, so the speed, times the magnitude of the magnetic field, times sine of the angle between them, but we're only going to consider the case where sine theta is equal to sine 90, so that's just going to be 1. So for our case, FB is equal to QVB. And we know that for uniform circular motion, the centripetal force is equal to m times the centripetal acceleration, and the centripetal acceleration, so m times v squared over r. So now we have our radius. Now in the case where a charge is moving in circular uniform motion, or uniform circular motion, the centripetal force is equal to the magnetic force. And so FB, which is equal to QVB is equal to mv squared over r. And if we isolate for r, so we move r, multiply by r, and divide by QVB, then we get that r is equal to mv squared divided by QVB. Two of the v's cancel out, and we get a final expression for the radius of the circular motion of a charge, which is equal to mv divided by qb. So from this expression, if we have a larger mass for our particle, then it's going to have a larger radius. If it's moving at a larger speed, then it's also going to have a larger radius. If the charge increases, then it's going to have a smaller radius. And if the magnetic field increases in magnitude, we also have a smaller radius. So now ready for an example. We have a particle and antiparticle pair separate such that the positive charge is moving to the left and the negative one to the right. If they're within a uniform inwards magnetic field of 0.75 teslas, we want to find the time before they annihilate each other, and all that means is the time before they meet up again. We're told to assume both their masses to be 8 times 10 to the negative 27 kilograms, and their charges, or charge magnitudes, to be 1.6 times 10 to the negative 19 coulombs. So if we draw our magnetic field, it's inwards, so that's going to be represented by x's. Then we can draw our charge. So our positive charge is moving to the left with some velocity that we're not told. And our negative charge is moving to the right with some velocity also that we're not told. But we'll assume that this is the same velocity since they're separating. So assume same velocity since they are separating. So the magnitude of our magnetic field is B equals 0.75 teslas. The masses of both these particles is 8 times 10 to the negative 27 kilograms. And their charges is Q equals 1.6 times 10 to the negative 19 coulombs in magnitude. So we can use our right hand rule. If we point our fingers in the direction of the magnetic field, so into the page, and we point our thumb in the direction of the velocity for the positive charge, so our thumb is going to go to the left, then our palm is facing downwards. So the positive charge is going to feel a force downwards, and so its circular path is going to look something like this. For the negative charge, once again our fingers are going to be pointing into the screen, and then we're going to point our thumb to the right. We see that our palm, in this case, if we point our thumb to the right, our palm faces upwards, so the force is upwards, but since it's a negative charge, the force is in the opposite direction, and so once again it's downwards. So our negative charge experiences a path like this. Since they're moving at equal velocities, we know that they're going to meet on the other side of this circular path. So this is their meetup point, where they're going to essentially annihilate. And we want to find the time before this happens. So we're trying to find delta t. We know the velocity, and we know that an expression for the time is delta t equals delta d, which is the displacement, divided by the velocity. Now in this case, both of them are going to be traveling half the circumference of their circular path. So in this case, delta d is equal to 1/2 the circumference of the circle, and the circumference is equal to 2 pi r. So there's 1/2 of 2 pi r. These 2's cancel, and so we know that delta d, or the displacement, the distance, not the displacement, the distance that they travel, is equal to pi r. So now we need an expression for the radius of this circle. We know from earlier that the radius of the circular path for a charge within a magnetic field, so r, our radius from earlier, r, is equal to the mass of the particle times its velocity divided by its charge times the magnitude of the field. So that's our radius. So if we sub all this in to our expression for the time, we have delta t is equal to delta d divided by v. Delta d is equal to pi r divided by v. So we have pi times the radius, which is mv, divided by qb, which is all divided by, so all of this is divided by the velocity. So it turns out in this question, these two velocities cancel out, and we do not need the velocity. The time is not velocity dependent. So we have our time is equal to pi times the mass of the particles, which is the same, divided by their charges and multiplied by the magnitude of the field. And if we sub in, this is equal to pi times the mass, which is 8 times 10 to the negative 27 kilograms, divided by q, or the charge, which is 1.6 times 10 to the negative 19 coulombs, multiplied by the magnetic field, so 0.75 teslas. And if you put that into your calculator, you'll get a final answer of 2.09 times 10 to the negative 7 seconds. So it takes 2.09 or 2.1 times 10 to the negative seconds before these particles meet up once again.